Let's learn the basics of set theory. Set is a collection of items that we'll call elements. A set will be denoted by a capital letter, like A. An example of a set is the set containing the numbers 1, 2, and 3. The 1, 2, and 3 are called the elements of the set A. And we want to say that a certain element belongs to a certain set, we can denote it by using this symbol, which means that 1 belongs to the set A. There are many examples of sets, and they contain all kinds of elements. For instance, the set B contains an elephant and a mouse. We can represent a set using a Venn diagram. It is labeled by the name of the set, and inside the ellipse, we put a dot for each element, which we also label. Next, we want to do operations on sets. The first operation, take the intersection of two sets. We'll denote it by A cap B. So let's draw two sets, A and B. Then the intersection of A and B is the collection of all elements that sit both in A and in B. Let's give an example. If A is the set with the elements 1, 2, 3, and B is the set with the elements 3, 4, and 5, and A intersection B set with the element 3. We can draw this explicitly, putting the element 3 in the middle, putting element 1, 2 on the left, 4 and 5 on the right. And these are sets A and B, and 3 lies in the intersection. The second operation on sets is to take their union. A union B is the collection of all sets, all elements, lie in either A or B. if we return to our example, in which A was the set containing 1, 2, 3, and B was the set containing 3, 4, 5, then A union B is the collection of elements 1, 2, 3, 4, and 5. Note that the order of these elements does not matter, firstly, and secondly, that we don't repeat elements. So the element 3 is not repeated. The third operation is subtraction of sets. Taking the difference. A minus B is the collection of all elements in A that don't sit in B. Again, in our example, we find that A minus B is the set with the elements 1 and 2. Finally, we can take the Cartesian product of sets. A times B, which is the set of all ordered pairs A and B, such that A is an element of A and B is an element of B. For example, in our example, we're going to have 9 elements in A times B. And it starts out with 1, 3, 1, 4, 1, 5, 2, 3, etc. Now we come to the advanced part. Let's do a few exercises and ask whether A union B union C, is it equal to A union B union C or not? Is A intersection B intersection C equal to A intersected with B intersection C? Is A intersection with B union C equal to A intersection with B union B intersection with C? And is A union B intersection with C equal to A union B intersection of A union B? The answer to these questions is yes. And you can do a proof by Venn diagrams. The only necessary hint is to realize that generic Venn diagram for sets A, B, C can be drawn like this. Finally, let's mention Russell's paradox. Which is just consider the set. Let's call it A of all sets that are not an element of themselves. Then it's not hard to see that if A is not an element of itself, it must belong to A. While if A is an element of itself, it cannot belong to A. Clearly, this is a paradox. And you can look up how mathematicians resolve this paradox by adopting new axioms for set theory. Examples of sets include n, the natural numbers, z, the integers, q, fractions, as well as r, the real numbers. Let's solve one of the exercises explicitly. Let's draw A, B, C. Let's try to prove that A intersection with B union C equals A intersection with B union A intersection with C. But first, let's do the left-hand side. So we take B union with C, that's everything that's here. Then we intersect with A. Which is this part. That's our final answer for the left-hand side. Now we do the right-hand side. We have A intersection B, which is this part. Then we have A intersection C. So that's A intersection C, which is this part. When we take their union, we indeed see that we get the same set as the one indicated in yellow. indeed this equation holds.